Okay. Welcome to my course, Bioreactor Engineering. So is the last lecture already for this set of slides. So it I will talk about how we use what we have learned so far, and then we look at the industrial perspective. So for the contents of the lecture, so it will be reactor engineering in perspective, and we talk about bioreactor configuration, and we how for the practical use of bioreactor, how we gonna use it, and how we gonna build this reactor. So we talk about how we monitor and control. So sometimes we use principle of control engineering to control our bioreactor. We look at the parameter that we want to control, and then finally we will summarize. Oh no, before that we are going to use sterilization, how we gonna clean the system, make it from germ, get rid of germ, something like that, and then I will summarize what we have learned so far. So in terms of bioreactor, so bioreactor is the heart of any fermenter or enzyme conversion process. So enzyme is a biocatalyst. So we use this catalyst in biological application. So design of bioreactor is very complex. So it's really based on rule of thumb. This one, and then sometimes it's like dimension kind of thing. For example, like this. So if we look at our course, so I have summary what this is just example like CSTR, how we gonna decide it. Like this one is like rule of thumb, so it's dimension from D and H. D is this one, H is height, for example, for CSTR, and the other things. And for the bubble column, we have this one is aleph. So we have this dimension ratio, also aspect ratio, for example, and we can calculate how do we decide. Actually, sometimes we begin with the volume first, and then after volume we change to this dimension, and we get some number. And sometimes in the real application we have to adjust this number as well. Like we don't have a tooth like this diameter, so we just try as close as we can. Okay, this is just example, so it's based on rule of thumb and then some dimension as well. This is how we consider when we design bioreactor. Is bioreactor configuration. For example, should the reactor is CSTR or air driven. Air driven is like I give you some example here. Is this one is bubble column, is one column with a gas inlet is called spatula, and we have liquid come in and come out as well. And the other one, if you have two tubes connect together, this one is upward, and then is called aleph bioreactor. It's called aleph bioreactor, and it's fall down here as well. Okay, and this one is conventional continuous stir tank reactor. So it's more common with the chemical engineering principle. So it has a cooling jacket, it has baffle, it has some feed here, and then this has a stirrer or agitator. For example, this driven by motor, but this one is air driven, so it has this configuration. okay, without mechanical, because sometimes we use this too because we want to get rid of this mechanical stirrer, because sometimes it's introduce some contamination to our system. For next process continue as inside reactor is we want to control temperature, pH, DO, dissolved oxygen, okay, and how parameter control, how with contamination, so we can control it, and how we can avoid contamination. For example, mode of operation is should be continuous, or we want to feed something in the middle, or we just use the batch process, for example. This is how we consider when we decide reactor. And as I mentioned about rule of thumb before, so we can use several handbook to identify the dimension. But after we decide, we need to consider the real application, the practical aspect as well about this one. And in perspective of when we want to produce things, you can adjust by number of money that you can produce. So it's if $1 per ton is 100 kilogram. So this your treat water is $1, and if you can produce some protein for like your what is called the vaccine, for example, it costs you a lot of money. It's like 100,000 100 million per ton, for example. Okay, if you produce some antibiotic, is between this like 500,000 US dollar per 1,000 kilogram, for example. So it's different kind of scale. So, and for the normal term, I will let you decide the product that you want to sell, for example. So, but unfortunately for this term, I cannot make it like that. So you can estimate your money earned from what product that you want to produce. And before that, we need to consider about the cost inside the bioprocesses. Okay, the total cost is from several sectors inside the company, like R&D, research and development, and for this is called manufacturing. This is come with our subject, which is bioreactor. See this one. So for the fermentation or bioreaction, so you have raw material, and for the operation of bioreactor, we have labor for the operator, for example. We have utilities, energy, water, steam, and waste, and then we have some depreciation, insurance, for example. And after you produce, you have downstream processing. You need to purify your product, for example, and it's come with material, labor, utility as well, and similar as production process. And after that, you need to market your product as well, because you want to sell to someone else which doesn't know technically about your work, for example. And if we split the cost for this one, R&D, maximize, speed up. Okay, it's how you scale up things, maximize productivity, okay, minimize contamination risk. Okay, this is if we break down about the cost. Okay, maximize substrate conversion. You want to convert as much as you can. You want to have more yield, for example. For the operation, you minimize reactor size, but you want to produce in a large number. Maximize catalyst concentration, for example. You want to maximize your yield, for example. And then this one, optimize reactor condition. Condition mean pH, temperature, for example, something like that. And you want to improve your strain, and then your media that you want to culture, you want to use it optimum as much as you can. And then for the downstream, you want to have your product as pure as you can. So you want to maximize product concentration, for example. And I give you some better idea about how the company work. This one is the vaccine production is mRNA vaccine production. For the first step, they produce mRNA. So you have mRNA template. This is bioreactor, and you have DNA, you have enzyme. Enzyme is catalyst, as I mentioned. So is try to use DNA template to make a lot of copy. Inside is enzyme RNA polymerase. Polymerase is something that you produce. Okay, you make mRNA as much as you can, and then you purify it, and see it's downstream already, like this one. And after that, after you produce mRNA, you need to put more ingredient. It's called LNP, lipid. So you wrap it with the lipid nanoparticle, and then you package it, and then after that you make some market. This is how they produce some mRNA for the vaccine COVID-19, for example. This one. Okay, this is how we work as an engineer in a company. Okay, engineer can contribute in many sector. And as the first thing, this one I already mentioned about it. This is CSTR, so you have many things. Spatial is the same thing. Air come to the spatial, and then if you have heat transfer, you have cooling water, something like this. You have foam baking. Sometimes it's with foam baking. You have aseptic, mean very clean. Okay, you have exhausted gas. Sometimes it's produce some CO2. So you want to remove this CO2 from your system. Okay, and then this is a conventional bubble column. And for the airlift bioreactor, you have many kind of things. This one is called internal is this one, internal loop vessel. This one is called external loop. The one is upward is called riser, and the thing that come down is called downcomer. This is similar thing. And then the spatial is where the air was introduced inside bioreactor, for example. This is bioreactor configuration, and actually there are many kind of bioreactors we use in industrial. This one is pack bed. Pack bed is pack of biocatalyst, for example. So you have something like this. You have spatial here, and then you pass your media here, and then you scroll some here, and they have exhausted here. And actually there are many kind of bioreactor. Some bioreactor you can use only once. It's called disposal bioreactor, for example. So you get rid of a lot of contamination for this one, for that one. So for the industrial bioreactor, sterilized operation are very important. Okay, sometimes it can withstand 3 atm and pressure is above atm, and the temperature is around 150 to 180 degrees Celsius. For the industrial bioreactor, we need to consider aseptic operation, how we clean the system. fermenter, inoculation and sample, for example, material of construction, structure design, and evaporation control, because sometimes we don't want our media to evaporate and you will lose some liquid from your system. And this is how they design the inoculum vessel. Inoculum is like you put more cell inside the fermenter. You need to have some amount before you feed into the fermenter. Do we have some example? Okay, this one. So you need to have some amount of cell first, so and then you put inside, and how they inoculate to the system. So they design this one. Okay, you have steam tap here as well to make it very clean. The air here, the air into the system should be sterile also, because some germ or some contaminant can come from the air as well. This is inoculum vessel. And this is sampling. Okay, they try to avoid contamination as much as they can, and then they have some valve to make sure that everything is clean by steam. Very high pressure, not very high. You should have some temperature and some pressure as well for the steam to clean the system. Before you have some sample. Otherwise, your fermenter is a contaminant with bacteria or something that you don't want to grow inside. After that, after we operate things, so we want to control. This one is based on feedback control, this one, and you measure some variable and then you adjust with the set point, and then you use controller to, sometimes they use PID control to control some variable that you want to control. And here is some control parameter inside Bioreactor. Sometimes you can control physical variable like temperature, pressure, level. Okay, foam, you don't want a lot. So this is physical things. Gas hold up mean how much gas inside the system. Some chemical, you want to control pH. You know that some pH is toxic to the cell, for example. Dissolve oxygen or dissolve CO2, for example. Conductivity. Okay. And sometimes we want to consider the biological thing, biomass, concentration, enzyme, the catalyst, biomass composition. You produce some RNA, DNA, for example. Viability is how the cell viable or not. Is the cell dead already, for example? Morphology of the cell. So this is parameter that we want to control here. Is for the modern day you can even measure this thing, and for the previous generation you just measure some physical or chemical property inside Bioreactor. Okay, and here is the example of calculation. Okay, I will have a look, maybe one or two. So this is the first example, time for batch enzyme conversion. And enzyme is used to produce compound. Okay, and then this is a parameter of how the growth Vmax, okay, in this unit, and Kmax, Km is this unit, and we use milliliter mountain, for example. Plot the time, okay, for substrate conversion. Okay, initial S0 is this one, and convert in this Vmax. Okay, convert Vmax from this one Vmax, and then from this one to this one. Wait. Result from equation 10. Okay, and we have this one, percent of substrate. So we vary from substrate concentration. Substrate, you want to maximize your substrate as much as you can. See this one for this picture, and then you just vary from equation here, and this is the equation, right? Okay, from this equation, okay, this one, and you just plot this one. Okay, you check this equation, and this is the time that required to have your, this is your initial. See, if it's 0, it stay the same for the final. Boop, right? And you use this equation to plot the time that you need in terms of hours. And then you have this kind of plot. If you want, again, if you want to have more conversion, you need to wait quite long, like 5 hours for this 90 something conversion for the maximize. Okay, I will finish this lecture first, and then we continue in the part 2. Okay, enjoy, and then it's final lecture already. You should have some idea how we use the knowledge from this course in the industrial.